Hi everyone. In this video, I'm planning on finishing up the Chapter 7 presentation, though we might have a second video for Chapter 7 about fugacity. But I'd like to begin by reviewing a few things that we talked about last time with regards to Chapter 7. One of the things we talked about was the compression factor, Z. And I defined the compression factor for you as the molar volume that a real gas would have divided by the molar volume that an ideal gas would have at a given temperature and pressure. Okay, but of course we can just recast the denominator here in terms of PV, N, and R, and T, where Z becomes PVM real divided by RT. Now remember, Vm is just V divided by N. And so anytime we have a molar quantity like molar volume, molar Gibbs free energy, it's just the extensive volume or the extensive Gibbs free energy, for instance, divided by the number of moles, N. Okay, so let's take a look at this plot over here. The compression factor for an ideal gas is never going to change, and that's represented by this straight red line right here. No matter how we change the pressure of the system, the compression factor of an ideal gas is always going to be 1 because PV is always going to equal nRT. But for other gases, we're going to have deviations in terms of our compression factor. And a couple of the situations that we encounter are, if you consider the hydrogen gas and the helium gas on this plot, they always have compression factors that are higher than that ideal gas line. And if you recall from last time, we saw that that implies that the system is dominated by repulsive forces between particles. Okay, but then the other situation that we encounter for certain gases like methane, CO2, the compression factor kind of dips down for a while before rising back up again at high pressures. And that's just implying that for this region right here, for that gas, the attractive forces are dominating and making this molar volume lower than you would expect for an ideal gas at that pressure. Okay, but eventually when we get to a pressure that's high enough, the attractive forces get overwhelmed by repulsive forces, and that's when the curve really runs away and becomes higher than 1. Okay, skipping ahead here to slide number 12. I want to talk a little bit more about the Boyle temperature because that seemed to confuse quite a bit of people. So I'm just going to recreate that plot above and make sure that you understand the compression factor before you attempt to understand the Boyle temperature, because you really have to understand the compression factor to understand the Boyle temperature. So I'm going to make the same plot that we made on the previous slide. I've got compression factor on the y-axis, and I've got the pressure on the x-axis. Right there is a compression factor of 1, which corresponds to the ideal gas. And I'm going to start by drawing a curve that like what we saw in the previous slide. Maybe this is CO2, maybe this is methane, but whatever this curve means, it corresponds to a low temperature, okay? And at low temperatures, there is a region of pressure where the attractive forces are going to dominate. But now imagine that we raise the temperature a little bit. So the temperature goes up a bit, and then we raise it a little bit more. The curve is going to look like that. And then there's going to eventually come a temperature where the curve follows the dotted line for a little while before tilting upwards like that. And then at high temperatures, it's just going to come straight out and up rather, and just never kind of move along the dotted line. And that's going to correspond to regions where the temperature is high enough that the repulsive forces are completely dominating and the attractive forces don't matter at all. Now, for the particular temperature where the curve follows the dotted line for a little ways before curving upward, that right there is the Boyle temperature. Okay, and what I didn't mention last time is that we can calculate the Boyle temperature in terms of the van der Waals parameters for a gas. So for a van der Waals gas, this TB, Boyle temperature, is going to be equal to A divided by RB. Okay, and you know what A and B means for a van der Waals gas. You just look those up in the back of the book. But make sure that you're careful about your units again for this R constant. Okay, on this slide I want to talk about the law of corresponding states. And before we get to all those points up there, I want to draw for you a couple of different phase diagrams here. So these are going to be the pressure, temperature, phase diagrams. So we can call this one substance 1, and then the pressure and temperature for substance 2. All right, and you've seen these before. There's kind of a curve that goes like this, and then it hits the triple point, and then this coexistence curve comes up here to the critical point. Down here we have the gas phase, up here we have the liquid phase, and then here with low temperature, high pressure, we have the solid phase. Okay? Now let's think about the critical point for this particular substance. Right here is the critical temperature, and we can find its value. I don't know. Let's say that it's 200 Kelvin. Why not? And then right there, we have the critical pressure, and let's say that it's 5 bar of pressure right there. I just made those numbers up. I don't know what they correspond to, but let's just say that for a given substance, that's what they equal. Okay, then moving over here to substance 2, I'm going to write down its phase diagram, and it looks very much the same. It's got all the same phases, just like the other one. But of course, because it's a different substance, it's going to have a different critical temperature. So let's say that its critical temperature is 3,200 Kelvin. And then maybe its critical pressure is some different value than substance 1. Maybe it's equal to 650 bar, something like that. So each of these substances have a different critical pressure, different critical temperature. However, notice that the two plots I made look very much the same. The curves are almost identical. It's just that I had to zoom one or the other in order to be able to see the critical point on the same scale. And this is the key to understanding the law of corresponding states. The key is that if I take the pressure temperature phase diagram and just sort of zoom it or scale it such that their critical points kind of land in sort of the same spot on this phase diagram, then these curves are going to look fairly similar to one another. Okay? So that means that for any given substance, any given real gas, I could calculate the so-called reduced temperature by taking the temperature of the substance divided by its critical temperature. And I could do the same thing with pressure and do the same thing with the molar volume. That's the critical molar volume down there. And I could say that no matter what the gas is, it's going to be in the same phase, or it's going to have the same phase transition, the same coexistence for any of these values, as long as I'm dividing the system temperature by its critical temperature, or the system pressure by the critical pressure, or by the critical molar volume. And so let's take a look at this plot right here. I think this will help you understand what I'm trying to say here. On this axis, I've got that reduced pressure that I calculated for a number of different gases here. And so for each one of these, or whoever made this plot, took the pressure and then the pressure of the system, and divided by the critical pressure, and then just began plotting that PR right here. And then they put that on the x-axis and then put the compression factor on the y-axis. And you notice that no matter what the substance is, that for a given temperature, so here is TR equals 1, so that is right at the critical temperature. Notice that no matter what the substance is, no matter what the gas is, all of these data points are falling on the same curve, at least approximately. So that's what the law of corresponding states says. It's in a sense just for the given substance, you kind of zoom in or you zoom out depending on the critical temperature, critical pressure, critical molar volume, and they're all going to fall on the same curve if you plot their reduced pressure for against their reduced temperature. Okay, so what's kind of cool about the law of corresponding states is that Dewar, the scientist named Dewar, after whom the Dewar flask is named, used the law of corresponding states to predict the condensation temperature for a number of different gases before attempting to condense them to their liquid or solid states. And this was very helpful to him. He considered the law of corresponding states to be the most useful thing since the invention of the Carnot engine. And it was useful to him because he used the law of corresponding states to predict those condensation temperatures for a gas whose condensation temperature he didn't know yet. So he could get a guess at how cold he had to make the system in order to condense that gas, like hydrogen, for instance, or nitrogen. So anyway, the law of corresponding states is an empirical law, and it doesn't work. It doesn't work in all circumstances. It seems to work best for nonpolar spherical molecules, and it relies on empirical constants, so experimentally determined critical constants. Next up, I think I will make a separate video for the fugacity, so stay tuned for that.